Hello, welcome to the CIMAC Tech Talk. I'm Mark Schinke and I'm working for CIMAC as a project manager. I welcome all of you to our CIMAC Tech Talk about emission reduction today. I'm glad to welcome you back after our summer break. Today we are going to hear 4 different presentations. We are going to hear Mr. Ken Kawabe from Yanmar Holdings. We are going to hear Mr. Kutatus from Virtusense. We're going to hear Mr. Tsuda from the National Fishery University. And we are going to hear Mr. Beutsch from Wärtsilä. And today's moderator is going to be Mr. Peitz from Hook Engineering. I have to do some remarks before we start our presentation today. With the Tech Talk special, CIMAC would like to offer a platform for exchange. The presentations are an information offer of the respective author and or the company, and thus do not necessarily reflect CIMAC's opinion. On top of that, I want to make everybody aware that this session will be recorded and later on be available on the CIMAC website. And I'd like to encourage all of you to type your questions to the speakers in the chat so that we can have a lively discussion afterwards. I'd also recommend to you to already type out your questions during the presentation so that our moderator can review the most interesting questions and ask them to the speaker afterwards. With that being said, my introduction is done already, and I'd like to hand over the voice to Mr. Peitz, who is going to lead us through the Tech Talk session today.
So welcome all, also from my side. I'm Daniel Peitz, working for Hook Engineering, and I have the honors to present to you today's edition of the Tech Talk on emissions. And hopefully you had also a chance to enjoy the summer break. Remember, now it's only no more summer break before the next CIMAC Congress. You can still also submit abstracts for it until end of September. And today, as a small appetizer for next year's Congress, we will have some presentation. The first one will be from Ken Kawabe of Yanmar about IMO Tier 3 SCR system, and in particular the operation also in Tier 2 zones. And with this, I would please ask Kawabe-san to present his presentation.
Okay, thank you very much for the introduction. And I already share my screen. So can you see my screen?
Yes, we can.
Okay. So I would like to start my presentation. I'm Ken Kawabe from Yanmar Holdings. My presentation title is a study on deterioration mechanism of SCR catalyst during bypass operation for marine diesel engines. And the background is here. As everyone knows, the IMO emission standards took effect in the NOx emission control area called NECA from 2016. And North Sea and Baltic Sea were added from January 1st, 2021. IMO 3 NOx emission reduction level is 80% relative IMO Tier 1. And ammonia SCR is widely used technology for IMO 3 emission compliance. In NECA, compliance with the IMO 3 emission is required, and SCR system is activated with low sulfur fuel. Outside NECA, the Tier 2 level is applied. It is not mandatory to activate the SCR system. In most cases, a marine engine runs on the low-grade fuels such as HFO, LSHFO, meaning that the exhaust gas contains high levels of combustion residue and SOx. And if SCR catalyst is exposed to HFO fuel exhaust gas, the catalysts are deteriorated by sulfur ash and oxide formation in catalyst pore. In addition, the fuel consumption is worsened due to the high back pressure. So typical solution of dealing with this solution, bypass system has been widely used for protecting catalysts from the HFL exhaust gas outside NECA. The bypass operation practice would require a way for the exhaust gas to bypass the catalyst reactor. The doubling the amount piping are required. It is more difficult to install in ship with multiple engines. To address this, Yanmar set out to reduce the total system size by making the bypass channels smaller, devising the integrated bypass and catalyst reactor unit shown in here. This makes it possible to make system more compact while maintaining the advantage of the bypass method, such as a long catalyst life, low back pressure, and redundancy. So, however, the SCR catalyst deterioration during bypass operation with integrated SCR system was occurred during the development phase. We reported this issue in CIMAC 2019 paper. However, Yanmar did not report catalyst deterioration mechanism in detail. That deterioration was caused by exposure of catalyst of high sulfur HFL exhaust gas under condition mid or low temperature condition around 100 to 200 degrees C and almost no gas flow. The possible catalyst deterioration mechanism during bypass operation is three: ammonia bisulfate formation and metal sulfate formation, and corrosion and collapse catalyst structure by sulfuric acid. In this presentation, I will present the main root cause the deterioration during bypass operation in detail. I will explain onboard ship test condition. Onboard test was conducted to check the catalyst deterioration under actual use bypass condition in ocean-going vessel auxiliary engine. SCR operations and tested SCR system are shown here. And the engine was started and stopped several times according to sea power generation demand. Fuel of bypass operation HF4 and the total time of bypass hour 6 months. And the fuel type was HF. And the reactor was prototype integrated bypass system with vanadium-based catalyst, honeycomb-shaped substrate with square cells. And the NOx conversion tests were done the small core samples which were picked up from the ship as shown here. The ship tested catalysts were installed in 2 layers. The first layer is upstream close to the engine, and second layer is downstream. And the sample were for first upstream, first downstream, second upstream, second downstream in order from the upstream side closest engine. NOx conversion check was done by the synthetic gas test bench. Here shows the system, a schematic diagram of the synthetic gas test bench here. And the testing condition was shown in these tables. And the checked sample were 5 samples, including that fresh and aged 6 months bypass operation. And synthetic gas test reactor space velocity condition is 30,000 and ammonia NR was 1. Here shows the NOx conversion result in here. Please see right-hand side. Vertical axis shows the fresh and aged sample location from the upstreams. And the horizontal axis shows the NOx conversion at 200 degrees C and 250 degrees C with ANR1 at space-based 30,000. Comparing to the fresh catalyst, second layer NOx conversion was severely deteriorated. On the other hand, first layer sample were not deteriorated. CFD simulation shows the exhaust gas flow backflow in the second layer catalyst. Considering the CFD result, NOx conversion degradation are strongly correlated with HFO exhaust gas backflow. Next, the various chemical analyses were conducted to understand the mechanism. Here, the concentration a correlation between NOx conversion and bulk sulfur contents. Sulfur content analysis were done by the carbon sulfur analyzer. And you can easily see that NOx conversion is decreased in proportion to the amount of bulk sulfur. So the NOx conversion degradation are strongly correlated with bulk sulfur content. In order to the possibility of ammonium sulfate formation, the amount of ammonia ion adhering the catalyst were analyzed. Analysis were conducted by ion chromatograph measurement of aqueous solution after washing the sample. The horizontal axis is ammonia ion concentration after water washing. As you can see, there is no correlation between NOx conversion and ammonia ion concentration. This indicates that ammonium sulfate, bisulfate formation is not the main root cause. And the next catalyst catalyst surface analysis were conducted by mercury porosimetry and BET method. The correlation between NOx conversion and the relative surface area degradation is here. Horizontal axis is relative sulfur area degradation compared to the fresh one. You can see the NOx conversion is decreased in proportion to the relative surface area degradation. That NOx conversion are strongly correlated with the catalyst surface area. We think the catalyst pore clogging or disappearance collapse are assumed. The next one, adhesive metal components analysis were conducted by using the FEEPMA. Vertical axis is the relative difference amount in adhering metal components. If this relative value is greater than 1, it indicates that adhering deposit is increased. And sulfur and oxygen increased, but no significant increase of components containing HFO such as calcium, silica, and Panagia. From this result, the clogging catalyst pore due to sulfur ash such as calcium SO4 may not be major root cause. It seems to be a deterioration due to other contents such as sulfuric acid. And here also the increase in aluminum probably came from the aluminum fiber to give the physical strength to the catalyst or insulation mat of the catalyst. Next shows the degree of condition difference inside the catalyst were confirmed by the FEPM analysis. Here shows the fresh and aged sample vanadium and sulfur. Red color is indicate high concentration and low is low concentration. The aged catalyst was observed that the vanadium amount relative smaller near surface, but amount of change deep inside is not so large. The near surface difference is due to the large amount of sulfur adhesion, maybe. And this indicated the not big loss of vanadium metal was occurred. On the other hand, sulfur seems to be penetrated deep into the catalyst from the surface, and it looks like there are some cracks in the catalyst. This indicates the possibility that the catalyst corrosion had occurred by sulfuric acid. So next, a visual inspection check and the corrosion element test were conducted. To see the left side visual inspection picture, it was found the erosion of catalyst components in the insulation mat. And element tests were conducted to determine which sulfuric acid corrodes the catalyst. The left side picture is by the diluted sulfuric acid. Right side picture is by concentrated sulfuric acid. The catalyst was found to corrode when exposed to concentrated sulfuric acid. And based on this result, assumed catalyst deterioration mechanism during bypass operation is shown here. Ammonium sulfate formation and metal sulfate and oxide formation are not major root cause. And the corrosion of catalyst by sulfuric acid may be the main root cause. Assumed mechanism is following. First, sulfuric acid, sulfur and SO2 is oxidized to the SO3 on the vanadium metal. Then sulfuric acid is formed at the location below sulfuric acid dew point temperature during bypass operation and engine stop condition. And then the sulfur is concentrated to concentrated sulfuric acid in mid to low temperature during bypass operation with engine run. Finally, the concentrated sulfuric acid reversibly corrodes the catalyst and the insulation mat. And Yamaha took countermeasures shown here based on the deterioration and mechanism understanding to prevent the irreversible catalyst deterioration by backflow. And the reactor structure was optimized by adding the perforated metal plate to minimize backflow and optimized purged air in here control to minimize the backflow. And optimize periodic valve open during bypass operation to purge sulfur by exhaust gas heat for preventing concentrated sulfuric acid formation here. So here is our conclusion. And in long-term bypass operation with HFL irreversible catalyst deterioration was observed that caused severe NOx reduction conversion degradation. This was caused by the concentrated sulfuric acid corrosion. Yamaha has succeeded to optimize off-bypass integrated reactor structure and controls based on this mechanism understanding. And then Yamaha has delivered more than the SCR 1,500 units into the market. We think SCR continue to be an important technology for decarbonized fuel ships. Yamaha will continue to improve our SCR in order to provide the customer with best solutions. So that's all. Thank you very much. And this is end of my presentation.
Thank you very much, Kawabe-san. And as I currently don't see any questions in our chat, I would encourage all participants to write the questions. We can then read them out to the contributor. In the meantime, maybe to get the discussion started, I would like to congratulate you on finding this root cause for the catalyst deactivation. As I remember, on the last CIMAC Congress, there was still quite a bit of discussion whether these elegant designs with only valves at the inlet of the SCR reactor, but no closing valve at the outlet, would in reality be not affected by this catalyst deactivation as you have shown. Now, as a countermeasure, you introduce the perforated plate, which of course is bringing back pressure. And also you introduce the regular flushing and heating of the catalyst. Did you also consider other measures to actually get rid of the issue completely?
Sorry. So let me confirm that your question clearly.
So the countermeasure today are perforated metal plates and regular heating of the catalyst.
Yes.
Did you also consider other measures as actually going for an outlet closing valve?
So and basically we use perforated metal and optimize the valve control, and in sometimes we have the option for the closing valve outlet side, depending on the customer's demands.
Okay, thank you. So it is there as an option.
Yes.
Maybe also, as you observed sulfuric acid-induced corrosion of the catalyst, did you also see issues with the reactor itself as part of the reactor is cold? The steel corrosion?
Still, no, we do not see that critical corrosion in our system in the market.
Okay, thank you. Thank you very much. We have also a question from the chat, and it is, what type of injector do you use?
And the injector means a urea injector, and urea injector.
I would assume so. Yeah.
Yes. Our urea injector is air-assisted injector. We use in this system. Is it?
Yes.
Okay.
I believe so. I don't see a follow-up question to that, but there is another question. Are the used SCR catalysts coated catalysts or fully extruded catalysts?
Okay. So basically extruded catalyst we use in here. No, not to use coated catalyst.
Thank you. That should answer the question. There's another question. How did you judge the heating benefit versus bringing in additional sulfur and dust, etc., by opening the valve periodically? As when you are sometimes opening up, then also you will have high sulfur fuel operation with contaminants reaching the catalyst, I suppose.
Okay. So, and in the basically when we open the valve for prevent that irreversible catalyst deterioration, and fuel is most of the case fuel is switched to the low sulfur fuel. So this means is it answering the question? I think So,
I think that partially answers the question. So during the regular opening up for heating out the sulfur from the catalyst, you would require, for this instant, a switch back to low sulfur fuel. Okay, then I guess you have developed a routine for the minimum holding time to heat out also the sulfur contained in the catalyst and accumulated at that point. Okay. For the moment, I don't see any additional question in the chat. And yeah, it seems it's very clear. And thank you very much for your contribution and also for sharing the detailed investigations on the postmortem catalyst analysis with us. Thank you.
Thank you. Thank you very much.
So then I would like to move over to our next speaker, which will be Panagiotis Ketatos, and he will be presenting the concept of advanced SCR control by utilizing virtual sensor concepts, where the state of the SCR catalyst can be a feedback also to the engine operation. And yeah, this very advanced and promising SCR and engine control system has been investigated together also with the Paul Scherrer Institute as an academic institute. And I would like to give the stage to Panos, please.
Thank you, Daniel. I hope everyone can hear me and you can also see my screen.
Yes.
Perfect. So good afternoon to everyone joining from Europe. Good evening to those in Asia and good morning to those in the Americas. And thank you very much to the organizers for inviting us to contribute to these tech talks. Today I will be presenting you the work that we did on combined engine and SCR optimization. This work is the result of many people, the collaboration mainly of two Swiss companies, Virtusense and Hug Engineering, and the Paul Scherrer Institute in Switzerland. And you can see in the screen here, let me just use a pointer, quite a few names who has contributed to this, and I thank all the co-authors for their contributions. So let me start briefly by introducing our company, Virtusense. We are a software company, and we combine physical modeling with machine learning techniques to provide cost-effective, reliable visual sensors for control, monitoring, or as backup to physical sensors for the marine and power generation sectors. So our visual sensors aim to enhance and extend the existing sensors and also provide reliability and accuracy for sensing what is otherwise difficult to measure, such as emissions or fuel characteristics or pressures at very high pressures. So we work together with engine makers and designers and part suppliers for emission control applications. Let me just find my cursor again. Okay. Looking into fuel flexibility and controls or fuel flexible engines, condition monitoring of components on the engines, and providing simulation plugins for engine design and optimization. So this was a brief overview, and jumping directly into the main content. So to introduce a bit the problem that we're trying to solve with this project. So most modern engine installations require an SCR catalyst to reduce engine out NOx emissions, and in order to comply with environmental regulations, which are becoming ever stricter, obviously, and the SCR system is a very effective way to lower NOx emissions, and it can lower typically well above 90% of the engine out NOx emissions in the after treatment using precise dosing of a reducing agent, typically urea, which is converted into ammonia in the catalyst and in the exhaust. So traditionally in all marine and many stationary applications, the control of the urea dosing is based on what we say here a static map, which is a map of dosing of ammonia or urea depending on engine speed and load. And although this is a very simple and well trusted system, it's very effective. It's also easy to check for compliance. The downside is that when using such a system, it's not necessary that engine and SCR are very well optimized together. And this can also have very bad effects during the transient operation of the engine, where jumps in NOx emissions or temperature can lead to high slip of ammonia or high NOx peaks in the exhaust. And a typical example of how this is bad is in marine applications in particular, where typically the engine will be a tier 2 engine, which is specifically optimized to not run with an SCR system. And then we just couple it with an SCR system to make it a tier 3 engine, whereby the reduction of NOx required in this process is closer to 60%, and it's far below the capacity of the SCR. And so we lose essentially the capability to optimize the two together, which leads to excess fuel consumption. And since the engine effectively is detuned from its optimal point in order to achieve tier 2 by itself. So how are we trying to solve this? In this project, we try to explore the capabilities of the combined fuel consumption and emission reduction using a combined, essentially, SCR engine control system. The final result is what we call intelligent SCR, and it involves effectively two parts. One is the optimization of the engine to be matched to a specific catalyst. This is the first part. And the second part is the active control of the maps on the engine in order to fit essentially the operation of the real-time state of the engine and the SCR in order to effectively reduce any peaks that might arise because of inability to match the operation of the engine to the state of the SCR at any given point. So what we aim to achieve with this overall intelligent SCR system is three things: overall emission reduction, and this includes CO2 emissions and NOx emissions, that is, reduce fuel consumption and reduce NOx emissions, and be able to effectively use either smaller catalysts with the same effectiveness or even better effectiveness than a bigger catalyst using intelligent control systems, or also use a less reactive catalyst. So these are the goals, and I will show you in the end how we did on this. So just a few things about the procedure of how this is done in the intelligent SCR system. So essentially the building blocks of what we need to do. The first part is to offline optimize the engine and urea dosing parameters in order to achieve minimum fuel consumption with the specific catalyst that we have that we will be using. Essentially, this involves fitting essentially the engine parameters to the emission standards that we require and the specific catalyst, and I will explain later on how we do this. And the second part is the online optimization, where the urea dosing is based on the catalyst state and the engine emissions at that given point. So for the engine part, what we used is essentially we built a full digital twin of the engine using thermodynamic models and artificial intelligence, mostly for the modeling of the turbocharger and the wastegate system. And for the so this is the first part, and for the second part, for the continuous monitoring that is required for the engine out emissions in order to be able to control the SCR, we use the VirtuSense NOx PVS, which is a physically assisted virtual sensor, which combines effectively the advantages of a physical sensor mounted in the exhaust and a virtual sensor which runs in a computer separately. So this works as follows. During the continuous operation of the engine, the virtual sensor provides a continuous NOx value, and so we have always a value of the NOx that is expected from the engine, and a physical sensor is protected from the exhaust gases, and we sample intermittently in order to retune the virtual sensor to always have an accurate output. So we have both advantages of the virtual and the physical sensor. The advantage of the virtual sensor is effectively unlimited reliability and the accuracy from the physical sensor. Overall, we have seen that this leads to a superior lifetime of the overall sensor and compared to other systems, and we have seen the extension of the sensor lifetime. Typically, zirconia-based sensors in the exhaust with high sulfur fuel will last a few tens or hundreds of hours, and with our system we can extend that to a few thousands of hours. So this is a big advantage. Now on the SCR side and the SCR models, our colleagues from Hug Engineering worked with colleagues from Paul Scherrer Institute to obtain static and transient measurements of the different catalysts, and the resulting models are able to capture both the static performance of the catalyst depending on the temperature and the space velocity. This is what you see here on this map, but also the transient performance of the catalyst that you see here with rapid changes in urea dosing or incoming gas temperature. And finally, to show you the test facility that we tested everything in. So all the systems were tested on a large engine research facility at the Paul Scherrer Institute in Switzerland. The facility houses a 1 megawatt medium speed common rail diesel engine with a prototype 2-stage turbocharging system. And the facility has an adapted ECU in order to be able to actively change parameters on the ECU. In this circumstance, we were changing start of injection to adapt the NOx fuel consumption trade-off, and the wastegate to mostly adapt peak pressure, exhaust temperature, and exhaust flow rate. And the engine and all the system, the SCR, were tested using a standardized cycle that we created, which has specific characteristics. The cycle, you can see it here, it lasts around 5 hours, and it has a first section of constant loads where everything is stabilized in order to mimic stationary and marine applications. And then we have some step responses where very fast and rapid changes in load happen from one load to another load in order to test the reaction of the catalyst and all the control systems. And finally, we have a transient area where we effectively mimic distributed power generation sector, where we have sudden load changes to follow the grid production and demand. Now, for the offline optimization, we built essentially a whole virtual testbed in order to be able to model everything and to optimize the engine parameters and the urea dosing. And through this, we effectively made new maps for the engine, static maps effectively for start of injection and wastegate, specifically tuned for a specific NOx reduction rate, but also for a specific catalyst, coupled to a specific catalyst. And we could also use this system in a hardware in the loop application to test all the algorithms that we were producing for the controls. And finally, once the offline optimization was completed and the specific maps for each specific catalyst engine combination were available, we also were able to test the online optimization on the engine. The online optimization essentially uses the offline maps, but also has online control loops to adapt the engine and SCR parameter maps and correct their settings by taking into account the current state of the engine and the catalyst. As an example, we can use, for instance, the cold start. During cold start, the temperature of the catalyst is low and increasing. This leads to effectively low conversion efficiency and ammonia desorption from the increase in temperature. So during this time, the engine controller will increase the engine out NOx emissions in order to consume the desorbed ammonia, while also the SCR will limit the urea injection. So this is an effective use of this. And to close to show you some results from the overall procedure and what we accomplished. So we used 3 different catalysts to test the setup. The first catalyst was what we used also for the reference, and it was tested first with the standard setup of using a map effectively as a normal feed forward for the NOx and urea dosing. And with this setup, we set it from tier 2, from the tier 2 engine settings, to achieve 90% reduction in raw NOx, and the result was 0.46 grams per kilowatt hour of NOx after the SCR for the whole cycle, average over the whole cycle, and 6.5 ppm of ammonia slip. These are obviously good results, but when we use the intelligent SCR compared to our baseline, we were able to decrease the fuel consumption by almost 2%, while at the same time decreasing by more than halving essentially the SCR out NOx, and decreasing by 40% the ammonia slip. So you see that even though we have a good result here, by optimizing together the engine and the SCR system and using this online control, we're able to really reduce the fuel consumption and the NOx at the same time, escaping essentially the trade-off between the two that is typically seen. What we can also do is, and we tested this, we tested the less reactive catalyst, where we use less precious metals on the catalyst, and we achieved with this catalyst also a lowering of fuel consumption compared to the baseline, and lowering of engine out, or SCR out, I should say, NOx and ammonia slip. And finally, just to showcase the capability of changing the parameters with different catalysts, we also, for a 33% smaller catalyst by volume, we also achieved lower fuel consumption and lower engine out or SCR out NOx compared to the baseline. So overall, what we observe is that the intelligent SCR system, this combined optimization of the engine and the catalyst and the controls, can achieve simultaneous reduction of fuel consumption and NOx, allowing us to reach lower emission levels, or allowing us to use either smaller catalysts or less reactive catalysts, which are also more robust. So with that, I would like to close. And first of all, I would like to thank all our collaborators and the co-authors of this work from Hug Engineering and Paul Scherrer Institute. And also I would like to thank the funding agencies who funded these 2 projects that led to the result that you saw today. On the one hand, the Swiss Federal Office of Energy and the Swiss Federal Office for the Environment. So with that, I would like to close, and I would happily answer any questions that there might be.
So thank you, Panos, for this very nice presentation, showing actually the possibilities if engine and after treatment are combinedly optimized for the best. And it seemed to have an impression on our audience. So far, there are no questions, but again, I would like to encourage you to post them in the chat. And in the meantime, maybe as a starter, we have seen, as you mentioned in the beginning, that the first generation SCR systems in IMO Tier 3 were quite well robust designed, but not so advanced in terms of actually control systems. Do you see also possibilities for upgrading them, as we have now quite a number of systems out there, at least with the first step, so the PVS system?
Yes, that's a good question, because I mean, to have a big effect, you do need to approach also the existing installation. So I would say a first step might be to have a monitoring system for engine out and SCR out NOx emissions in order to be able to effectively capture any mismatching of the engine control system and the engine state at that point and the SCR control system. This effectively gets rid of problems of transient operation, but also aging through some feedback loops. This is maybe a first step that is possible just from the SCR side. Now, for the combined system, I think it's too cumbersome to replace effectively the whole engine control system with the new control system. I think this is not practically applicable, and so work needs to be done effectively from the engine makers to provide solutions for this. But yeah, we need to see. It depends also on the incentives and on the requirements that are specific industries obviously already have requirements for feedback control of the SCR, and so for specific applications this is a non-issue. For marine applications in particular, I think this is a wider issue, but also it depends how long the specific installation is functioning within engine within ECA zones and outside ECA zones. So it depends really on the application.
Thank you. Actually, in the meantime, we received kind of the same question in the chat. So whether it would be suitable for retrofit of existing engine systems. Other than that, I still encourage you to post your questions in the chat. Yeah, we can ask them to the presenter. Otherwise, when we are considering these control systems, yeah, having the insight into the SCR catalyst operation, like you made up a full digital twin of the SCR, also of the engine, is it on this level something you would see in the future for us to reach also lower emission limits? Because you have shown that on this test engine, you basically reached something level-wise. It was not only IMO Tier 3, but it was basically at the end another 80% less SCR than IMO Tier 3. So that's quite an impressive result you achieved. And we see, of course, that outside the marine world, emission requirements can be a lot more harsh than just IMO Tier 3. So do you think it could be a key enabler to go for this more intense combination of the control systems, engine and after treatment, to get to these low levels?
Yes, that's a very good question. I think absolutely the ability to optimize something without engine testbed time is important, and also I would think that everybody by now uses simulations to optimize their setups. It's more and more important, especially since different applications which uses the same or very similar engines have different emission requirements also, and so it requires also a specific tuning for each individual engine. And once you go into combined engine and SCR optimization, then because the number of units produced are even lower, then you need to base more and more of the development and the optimization to replace essentially testbed time with simulation models. So I think this is necessary. I think that the tools are out there and available in general. I think that for the engine simulations, there are a lot of commercial tools also, maybe not so much for very accurate NOx modeling, but nevertheless, I think that you don't either need a very high accuracy for that. I think for the SCR side, I'm not so sure what is available, and also what the problem is that the different designs of the SCR and the different chemistry, the surface chemistry, but also the aging of the catalyst requires different capabilities in terms of modeling and also adapting the model based on the measurements. And so this maybe with more use of machine learning, we will be able to overcome that to essentially replace very, very difficult models which don't represent reality sometimes with machine learning models based on measurements. And I think this might be a shift that might happen at some point soon in order to facilitate the use of more simulation tools in this area.
Okay, thank you very much for this answer. We received then two more questions. One is where is this technology already used on real-world applications? If so, on which applications?
That's a good question. I think that this type of feedback control is very widely used, particularly in automotive applications and smaller engines. I think that the big problem with larger engines is the type of fuels that are used, which do not allow very cheap and readily available sensors to be used for feedback control. This is what we're trying to solve with the PVS system that we have, where we essentially use a relatively simple automotive type NOx sensor, but also protect it for environments that have high sulfur and high ash in order to reduce the exposure and increase the lifetime. So this is a problem. This type of system that we have here is very similar to applications that you can see in automotive applications, but applied in a different way in the marine industry or the stationary power generation, where the peripherals essentially and also the requirements for lifetime are different.
Okay, thank you. And actually, a very last one, and regards to time, we need to watch a bit. What volume compared to engine displacement should the catalyst have in order to achieve such high reduction rates as you did?
Well, that is a difficult question. I will have to get back to anybody that would like to ask. I think that you can go to our website. We have an info page also. An info email. I'm unfortunately did not put it in this slide, but to ask me that question, because I actually don't know the volume of the catalyst. I would need to look into it to see how big the catalyst was, but it was essentially, we chose the catalyst so that we can achieve it would be a typical catalyst application with this type of engine for a typical marine application. This is my recollection, but I will have to get back to you on that.
Thank you. Then with this, I would like to thank you once again for your excellent presentation and detailed answers, and would like to move over to our next speaker. Next speaker will be Minoru Tsuda-san from the Japanese National Fisheries, and he will be talking about black carbon abatement technology. So different technology paths, kind of with the fuel water, fuel additive, and also particle filters. And would like to hand over the stage to you. So Tsuda-san, please, we wait for your presentation. We can already see you and see your screen.
Thank you for your kind introduction. And good morning and good afternoon, ladies and gentlemen. My name is Kazuyuki Maeda, Professor Emeritus of National Fisheries University. The title of this presentation is Development of Black Carbon Zero System for Marine Diesel Engines. あ、こっち切り替わっちゃったね。どうしたらいいかな。これ、いいで。あ、これはパワーポイント。これは、まず画面小さく。これなんかあれだ。これ画面をちょっと小さくしよう。
Can currently see your second slide, and we can also see your cursor.
なんで
これ緑ですか？はい。
これ
はい。
これでいい。
カメラをまず。
はい。これを消したい
の。これこのオリジナルこれです。はい。
はい。真っ黒なった
そうです。これです。
これはい。カメラ
はい。それで、あとこれクリックするって。
Sorry。これは
カメラだけあれ画面共有する。なってないです。遅いです。なりました。
Sorry. Marine transport is a necessary component of any economy. Unfortunately, high-powered engines are required in ocean-going vessels, and these tend to emit large quantities of air pollutant and greenhouse gases. In order to prevent air pollution and global warming, reductions in the NOx, PM, and CO emissions produced by such vessels are urgently required. Because the ice in the Arctic Ocean decreases due to the global warming, Arctic sea route is under consideration. If this is realized, the distance between East Asia and Europe will be 30% to 40% shorter, and the risk of present sea route are reduced. For example, the risk of pirates in the Strait of Malacca and pirates risk off the coast of Somalia. And risk of travel in the Suez Canal. 切り替わった？遅いね。まだ。まだ切り替わる。Okay. In response to this, it's concerned about the following. Black carbon exhausted from marine diesel engines has the property of absorbing sunlight, so it heats the atmosphere and stays on snow or ice and keep melting it. As a result, black carbon has the possibility of promotion of ice melting and accelerating the climate change. Look at this report. Black carbon will stay on the ice and melt the ice forever. まだ切れた。そうね。これやっぱりあれだ。Wi-Fi だから遅いんですね。Currently, black carbon restrictions are being considered by the International Maritime Organization, IMO. Because the Arctic Ocean is a closed area, research to reduce black carbon to zero is urgently requested. This figure shows the outline of the newly developed black carbon zero system. This system consists of 5 steps. First step is water is added to the fuel to decrease black carbon. And second step is catalyst is added to the fuel to decrease black carbon. And third step to catch most black carbon in the exhaust gas, DPF is set up. And the fourth step to remove the black carbon in the DPF, a conversion equipment is set up. And the last step to remove the ash, a cleaning device is set up. First of all, I'll explain the first step. Water is added to the fuel to decrease black carbon generation in the combustion chamber during the first combustion process. This figure shows the process in which the injected fuel formed mixed air. This entering air. The higher the ratio of air to fuel in mixed air, the better the combustion. To be more specific, in the case of air, fuel only, end-to-end air corresponding to the fuel will be introduced. In the case of B, fuel with water. In the case of B, the amount of injection means fuel and water, increases as much as the water is mixed. The more the injection increases, the more the end-to-end air. As a result, combustion is improved by increasing end-to-end air against fuel. This figure shows PM reduction effect of water mixed fuel. Adding a ratio of 15% water to the total fuel can decrease black carbon generation by about 60%. This 15% water decrease 60% soot. Soot means black carbon. This figure shows the outline. This figure shows the second stage. Catalyst is added to the fuel to decrease black carbon. catalyst is added to the fuel to decrease black carbon generation in the combustion chamber during the first combustion process. Okay. This figure shows adding a CO2 catalyst to the fuel can decrease black carbon generation by about 20%. This figure shows properties of CO2. If the surrounding oxygen concentration is high, it absorbs and stores oxygen. On the other hand, if the surrounding oxygen concentration is low, it releases the oxygen that was stored. By utilizing this property, incomplete combustion can be improved. As a result, the production of black carbon decreases. I'll show you again. Add a CO2 catalyst to the fuel can decrease black carbon generation by about 20%. This figure shows the synergy between water and catalyst. This water catalyst, adding both water and catalyst to the fuel can decrease black carbon generation by about 20%. And the third, I'll explain to remove most black carbon, DPF is set up in the exhaust line. To remove most black carbon, including exhaust gas, a diesel particulate filter, DPF, is set up in the exhaust line. This figure shows the outline of PM reaction device installed in automobile. The PM reaction device consists of DOC and DPF, and catalyst is coated on DOC and DPF. This catalyst deteriorates due to sulfur, so this device can't be used on ships. For this reason, only DPF is equipped with exhaust pipe on ship. And all PM contained in the exhaust gas are coated by this DPF. This figure shows replacement of DPF on ship. This engine and DPF and the bypass line. DPF with generation function was installed in the exhaust pipe. This is this diagram of the newly developed DPF with generation combustor. This is combustor. Most of remaining black carbon can be removed by setting up a DPF in the exhaust line. This suit means black carbon without DPF and with DPF. Next, I'll explain the fourth step. To remove the black carbon in the DPF, a combustion equipment is set up. To remove the accumulated black carbon in the DPF, a combustion equipment is set up between engine and DPF. This figure shows increased fuel consumption due to DPF clocking. DPF clocking leads a decrease in exhaust gas volume. This decrease in exhaust gas volume leads a deterioration of supercharger performance. Supercharger revolution is low. This deterioration of supercharger performance leads reduction of air volume supplied to the engine. This is suction air pressure. This leads reduction of oxygen required for combustion. This is oxygen concentration. Reduce and deterioration of combustion. This leads deterioration of combustion. This shows increased fuel oil consumption. DPF inlet pressure high, fuel oil consumption, increased ratio of fuel oil consumption is high. This figure shows the required temperature for filter generation. From this figure, this 600 degree, 650 degree, 700 degree. From this figure, more than 650 degrees Celsius of temperature is required to remove the PM. This figure shows the DPF with regeneration system. DPF with regeneration function was installed in the exhaust pipe. This figure shows the regeneration effect of DPF. When DPF is blocked, the pressure in the exhaust pipe increases. Along with this, fuel consumption increases. This area is regeneration process of DPF. After regeneration process of DPF, the pressure and fuel consumption return to normal. Pressure to normal. Fuel consumption return to normal. Most of the black carbon accumulation in the DPF can be removed and burned in separation combustion. The effectiveness of this system was evaluated, and the following points were clarified. Adding a rate of 50% water to the total fuel can decrease black carbon generation by about 60%. 2. Adding both water and catalyst to the fuel can decrease black carbon generation by about 70%. 3. Most of the remaining black carbon can be removed by setting up a DPF in the exhaust line. 4. Most of the black carbon accumulation in the DPF can be removed and burned in a separate combustion apparatus set up between the engine and the DPF. Creation of a device that will remove the ash generated during the second combustion process is in an advanced development stage. Conclusions. Our proposed system has potential to reduce black carbon emissions from marine diesel engine to close to zero. Furthermore, since the global environment will not return to its original condition, even if it only deteriorates by a slight degree. We believe that all technical solutions, such as our proposal, that can minimize or eliminate further deterioration should be used to their maximum potential. Thank you for your attention.
Thank you very much. And actually, we have already one question in the chat, which is about the fuel penalty to clean the DPF at 650 centigrade with the burner periodically.
Yes.
Can you comment on this?
Remiges?
Yes, I believe the question is about the extra fuel penalty for heating.
Black carbons, how to black carbon? This 650 degrees Celsius, you mean? This it can be removed black carbon from DPF, but 600 degrees Celsius, it cannot be removed DPF from.
Yes. Do you have a number how much extra fuel is required for heating the DPF?
Heat? Oh. Okay.
The energy consumption for heating.
Oh, energy consumption. Yes. To reach the temperature, the combustor is used to use.
Yep.
Energy consumption. どれくらいの電力?
Otherwise, if you cannot comment right now on this question, we try to solve it afterwards.
Yes, yes.
That's okay. So
thank you.
The system is for regeneration, as you show on this slide number 31. You show there is a valve closing the DPF.
Slide number 31. Yes, this.
Yes, so element B is
element.
A valve. Left-hand side. The left figure, the piping figure.
This filter element is automobile's filter element use.
Okay. Thank you. On the other picture you have there with the cursor on the left. Okay. Maybe we take it actually later, as I see that the time is quite advanced. So once again, I would like to thank you for these very broad investigations, talking about water, fuel emulsion, then also catalyst in fuel, and also DPF and DPF regeneration. And unfortunately, we need to have some time still for our last presentation. So thank you once again.
Thank you.
And thank you. Sorry, ごめんなさい. Our next presenter will be Johan Boy from Wärtsilä, and it's a pleasure to have him here in this webinar, because actually it's on the occasion of the CIMAC working group for emission control technology, which has issued a new white paper on carbon capture, utilization of CO2 which is captured like this, and also storage. And you can find the paper on the CIMAC website of the working group emissions. And Johan will now take the chance to also share some of the key highlights of this new publication of CIMAC with us. So Johan, please, the stage is yours. We can see you. I see your microphone is also active, but not yet see your screen. Here we go.
Okay.
Thank you.
Okay. Good afternoon, good evening, and good morning, everybody. Let's now see where my presentation is. Okay. Now I assume you see my presentation. Is that correct?
Correct.
Good. Okay. I will now present this new CIMAC Working Group 5 paper on carbon capture, utilization, and storage. First, a few words about the intent of this. The intent is to give the reader an overview of the status, development needs, challenges still to overcome of these carbon capture, utilization, storage technologies. And the paper also contains a summary of existing activities that has reached piloting stage or seen as promising developments. Then we have also covered this direct air capture briefly. Currently a lot is happening in this field, and recent announcements of new projects, technologies in R&D phase are left out due to early development stage from this paper. But this paper contains quite a lot of links that if you want to really go into details, you can find a lot of literature and facts also from this information behind the links. But okay, let's now start. Do you see this screen, this slide, this CCUS chain overview?
Yes, we can see it.
Good. I just wanted to check that everything is working. Okay, fine. Okay, then we start. Here you see an overview of this chain. Let's start with this. Worldwide CO2 emissions from burning fossil fuels is 33 gigatons per year. It's quite a big amount. Then when we talk about carbon capture, today there are only around 20 big operation commercial CCUS plants in operation around the world, and they reduce only about 40 megatons per year of CO2. That's only something between 0.1 to 0.2% of the total emitted CO2 today. Then United Nations has said or estimated that about 6.3 gigatons per year CO2 needs to be reduced by year 2050. If we want to reach these climate targets that are prescribed nowadays. Okay, after the CO2 is captured, okay, then it has to be treated and then transported for the end use. Then today, if you talk about these carbon capture plants, okay, it's used mostly for this enhanced oil recovery. About 30 megatons per year is used for that, and the rest is then stored below the ground. That's about 7-8 tons per year, megatons per year. One big potential for the future, of course, is the utilization. Enhanced oil recovery is also part of this utilization. And today, about 80 tons per year is used for enhanced oil recovery around the world. That enhanced oil recovery could still be expanded with this carbon capture CO2 removed CO2. One other big potential, if we talk about utilization, is urea production, because today around 130 megatons per year of this CO2 is used for urea production for fertilizer. Okay, I said that by year 2050 we should need to reduce about 6.3 gigatons per year, and we need now to increase this fleet of existing or new CCUS installations then. Okay, now we take a look on the year 2020. Operating, under construction, advanced development, and announced in year 2020 was about 90 projects, but already in year 21 total amount had increased to 190. And this is still accelerating, because I read some day ago in a magazine that in Q2 of this year, the planned global carbon capture, utilization and storage capacity pipeline had already reached 905 million tons per year. That's something, 905, because the current capture rate is only 40 megatons per year at the moment. It will increase in the future. And what is the reason for this big interest then? It's of course to meet these national, regional, corporate net zero goals. Then the other is blue hydrogen production or low carbon hydrogen production. About 50 facilities are under development. And then investment incentives. And let's talk about two of these. The US 45K tax credit, it was recently expanded by the Inflation Reduction Act that was approved some week back in the United States. And now, okay, in the Inflation Reduction Act, about $369 billion is budget for climate and energy-related provisions is included. And now the tax credit is raised to about $85 per captured and sequestered CO2 metric ton, and to $60 for reused CO2. And if you apply this direct air capturing, the respective numbers are $180 per ton and $130 per ton. It's a big money. And these CCUS projects have to be constructed and start before 1st of January 2033. Then they can get this tax credit for 12 months. And let's then take this Longship project, what they have in Norway. The total budget here is quite big. It's 25 billion Norwegian kroners. That's about 1.8 billion euros. And in this Longship project, they have a target to have a full-scale CCS project to capture and store 4.8 million tons CO2 by year 2024. Part of this Longship project is also this Northern Lights, and that's a cross-border open source CO2 transport and storage network. In phase 1 in year 2025, they have as a target a capacity of 1.5 megatons per year to be captured and transported and stored. And the ambition is to increase this to about 5 million tons per year later on. And yesterday, they announced in these Northern Lights the world first commercial cross-border agreement. It's a project where 800 tons per year CO2 will be captured in a Dutch fertilizer plant, then transported and disposed on the seabed in Norway. That should be from year 2025. That this is now something that is growing very fast, this CCUS. Then talking about carbon capture types. The most, should we say, typical used ones is pre-combustion, is used for gasification and synfuel cleaning and for natural gas cleaning. But in this presentation now I will concentrate more on these post-combustion types. And when we talk about combustion type, the absorber technology is the most used one, the amine process, and that is actually major if we talk about the coal-fired power plant. Some features of this: the flue gas temperature needs to be quite a lot cooled down to about 50 degrees C, because the reactions are occurring at this temperature range in the scrubber. Then the flue gas should be cleaned. Here you see also some numbers. Sulfur dioxide concentration should be below 40 milligram per normic cubic meter. This means that in practice, if you have a coal-fired power plant, you need a DSOX, because otherwise you will start to degrade a lot of this amine reagent. And also the NO2 fraction of NOx should be below 50 milligram per normic cubic meter. And okay, with normal low NOx burners in a coal-fired power plants, these should be reachable, because only about max 5% of this NOx is NO2 typically. And then the third big thing is that this power consumption is quite high. It's reported that for a coal-fired power plant, about this efficiency drop is typically between 8 to 12%. That this is quite costly. And it's said that this carbon capture very often in this literature is shown that it's more than half of this reduction cost for the whole chain. It can even be higher, depends on the surrounding. Okay, let's then say a few words about this cryogenic carbon capturing. It's an emerging technique which might also be of interest for the marine sector, because here you cool the flue gas down very low to below minus 140 degrees C. Then you get this removed carbon dioxide in a solid form, and then it's compact. Another emerging technique which could be of interest is membrane, but that is today only commercial for these pre-combustion concepts, for instance, cleaning syngas or biogas or natural gas. And the major challenge, if you talk about flue gas, is the low CO2 fraction of the flue gas. It's only about 3 volume% if you burn natural gas, around 12% if you burn coal, and compared then to a natural gas containing sometimes up to 40 volume% of CO2, you see a very big difference. And a smaller concentration means also that you need a bigger absorber or filter, and you will consume more power for the same reduction rate. Then in this work, there's also a chapter about direct air capture, and the biggest facility today in the world is this Orca facility in Iceland, removing about 4,000 tons per year of CO2. And here you now see the examples what to do with this captured CO2. You store it, it's called sequestration, or you utilize it. Okay, enhanced oil recovery is considered as part of this utilization, or you can make synthetic fuels or fertilizers, but then you need a very clean CO2. Here you see this big potential with this utilization of this captured CO2, but as I said, then it needs to be clean. And nowadays, every year it's used 230 million tons of carbon dioxide, most of it used for fertilizer, 130 million tons per year, and enhanced oil recovery up to 80 million tons per year. Then this in the Orca facility in Iceland, they use this mineral carbonization. That means that magnesium and calcium silicates react with CO2 and carbonates are formed. In the Orca plant, this captured CO2 is mixed with water and injected into the ground, where it reacts with the rock, and then carbonates are formed. But this reaction is not fast, it takes 2 years. Then the third one here, the geological sequestration. There we store this CO2 underground in depleted oil and gas reservoirs. And this is well below the ground. It can be 1 kilometer or several kilometers below the ground. CO2 is compressed to about 100 bar pressure before it's injected. And then when talking about this geological sequestration, is very important to know this reservoir, because it needs to have a high porosity and permeability. And if it's consisting of sandstone or limestone, it's idle. And according to literature, these deep saline formations can store up to 10,000 gigatons of CO2. It's a large potential for the future. And then talking about these underground storages, one of the most well-known around the world is this Sleipner in Norway in the Utsira Formation, which started up in year 1996. But as I said, big assessment work is needed to secure the storage capacity and suitable of the formation, because otherwise incidents might happen. And in the paper, 2 small incidents are mentioned, Tordis and Visund oil fields, what happened in Norway in years 2007 and 2008, when injected oily water leaked out from the ground. Then on top of this, the robust legislation is to be in place, setting the frames for liabilities and funding. Next slide. Then if we talk about the power industry nowadays, the dynamics are very important. And here I now read the first sentence. If we increase the penetration of renewable energy sources, the challenges for the grid operators to maintain this electric reliability will arise due to this intermittency of wind and solar power, because if there is no wind, there is no wind power electricity. If there is no solar, there is no solar power electricity in the night, for instance. And therefore, thermal power plants are needed for this grid stabilization. And if you operate these on park loads, their efficiency is not the best. And then they emit also more CO2 emissions and consume more fuels. Therefore, power operators, such American ones, there are a few names mentioned, ERCOT for instance, they prefer non-spinning reserve plants. It means plants that can start very fast and be synchronized to the net and start to produce power at full load. And that should happen within 10 minutes. Now from the literature, can also be found some data about this dynamics of this amine carbon capture process. In Annex 3 here are numbers for a boiler and combined cycle gas turbine plant equipped with this amine carbon capture system shown, and a typical hot startup time is around 1 to 2 hours, and that's much longer than 10 minutes. It's too long. For instance, a gas-fired engine can start up within 2 to 10 minutes, reach full load and produce electricity, dependent on the engine type. And this means that this carbon capture technology is more suited for baseload plants such as a cement factory or a chemical plant. In recent years, this carbon capture has also gained interest in the marine sector. IMO, the International Marine Organization, has set a target for reaching at least 50% reduction of marine transportation greenhouse gas emissions by year 2050. And DNV Maritime has made a forecast that in year 2050, the carbon capture on board ships could reduce these greenhouse gas emissions by about 30%. It means a little more than 300 million tons per year. Quite a lot. Today then, in the marine sector, work is going on to pair experience from land-based technologies with knowledge in the maritime equipment industry. And the biggest challenge is in the marine sector is, you can see here, space. It should be compact. It should not consume too much power. That's for the equipment. And then for the carbon storage, it should not be consuming too much space either. And as I said, carbon capture technologies utilized on land are also looked on the marine sector, that they are now looking on this absorption technologies as amino scrubber, this cryogenic capture, and membrane is not on a commercial level still today. This needs still development. And here from the carbon storage, you can see that it could be in a liquid form or it could be in a solid form, for instance, from this cryogenic type. Then this port reception infrastructure needs also to be developed. You need to have a legal framework in existing in order how to have this rule, how to deal with this. Then in European Union, in this updating of this emission trading system, it has also been proposed that big marine ships should be included, that this could be a part of that process also later on. Here in the bottom now you see the status at the moment in the marine sector, that it's still in the early phase. Some design studies has been done, but some manufacturers has also already planned or even installed and tested pilot plants. And some of these suppliers also plan to have their first commercial installation in year 2024. And many of these marine carbon capture devices now seem to be done together with this sulfur dioxide scrubber, what they already installed on the ship. It will be combined with that. Okay, one word more about this carbon storage here. If you burn 1 ton of oil, you will get about 3 tons of removed CO2. That this is really critical, that this needs to be compact. Okay, then a few words about this technology, readiness of this technology. Okay, you can see this is from a source that was issued in year 2020, already 2 years ago. Okay, CO2 capture in the power generation. If you talk about a coal-fired power plant, it's in an early adaptation phase. Okay, some scale up needs still to be done, and then it's matured. It's almost already there. For natural gas containing less CO2 concentration compared to a flue gas from a coal-fired plant, there is still more work to do because this is only in the demonstration phase, that more testing is needed. Then regarding the transport, pipeline is major, and the ship port to port is in a demonstration phase. Some more testing needs to be done. And then ship port offshore only on the large prototype phase. That a lot of more work needs to be done. Then about the storage, enhanced oil recovery is major. And saline formation, early adaptation phase. Okay, or starts then almost to be measured also. Then regarding these depleted oil and gas reserves, only in the demonstration phase at the moment. Then for CO2 usage, urea is major, concrete early adaptation phase, synthetic methane demonstration phase, and synthetic liquid hydrocarbons large prototype phase. That a lot of developments still needs to be done. Okay, I just show this annexes very fast. Here is Annex 1 with its large-scale commercial carbon capture utilization storage projects in year 2020. In this list are 21 installations, and the big plant here, if it's a coal-fired power plant, it reduces a minimum 0.8 million tons per year, and if it's some other process, it's minimum 0.4 million tons per year. And you can see most of these are for enhanced oil and recovery, and then for some it is dedicated, then this means that they store it in the ground. And here is also one coal-fired power plant, Petronova, started to operate in year 2017, but it was closed down in year 2020 due to cost reasons. This is the only one in this list which is closed down. These other 21s are still operating. And here you see quite recent one from Canada for hydrogen production from year 2020. The first one in this list is from year 1972. And I said a few warning words about this storage well below ground level. Here is how it looks in the Tordis field in the North Sea. Here they injected oily water and they had a leakage. Then they discovered that this Utsira formation was not present in this region where they had injected this oily water. You can see it here, and therefore it happened. That you need to spend a lot of time and money on this pre-research before you start to inject CO2 below ground. Otherwise, these kind of incidents might occur. Then here you see the dynamics of this amine carbon capture system. Here is for a natural gas combined cycle. Here they say that this natural gas combined cycle without carbon capture, hot startup time 45 to 55 minutes. Okay. Nowadays, if they're optimized, they can do it in around 30-35 minutes. This is quite a long time. But then if you connect the carbon capture system here, then hot startup time increases to 1 to 2 hours. It means that this is a slow system to start up. But take a look on the ramp rates. Carbon capture system is as fast as the combined gas turbine combined cycle. That is fast when it's operating, but it takes time when you start it up. On membrane, CCS could of course be faster. You can take a look on this startup time, but it needs still to be developed, as I said. Here are some trends made by Bloomberg. And from here you see that these grid peakers, these more light ones here, will be the choice of the year 25. And these combined cycles, then number of those will start to decrease. Then these operating hours of these grid peaker plants and also this combined cycle plants will decrease quite a lot after year 25 when we have more of these intermittent renewable energies, solar and wind installed. This was my last slide that I stop now then.
Thank you, Johan, for sharing your expert view on the topic of carbon capture and utilization and storage. And we could just see today as well with the announcement of Equinor and Wintershall to build their CO2 pipeline connecting Germany and the potential future sites in Norway for the CO2 storage, that this topic is really picking up. But as you showed, of course, still quite some work must be done. For the moment, I don't see any questions in the chat. Again, encouraging our attendees to post them there. Otherwise, you talked a bit about the marine as a very difficult field for CCS technologies due to the constraints. And I mean, in contrast, you could indicate already a number of installations in the stationary. Do you see that now we would have a different situation with the IMO targets defined that it could lead to backwind for utilizing this technology as well in the marine?
My opinion or guess is that it will also become more common in the marine sector. It's about money, because if you can make money on this CO2 capture and you can save money on it, then you will start to do it. And especially now, I mentioned this emission trading system in European Union, that when now the big marine ships will very likely be included in that system, they have to do something. They have to start to reduce their CO2 emissions. And then this carbon capture could be one option for them. It's about money.
Okay, so you see it rather as a financial limitation rather than the technological aspects you raised for.
Daniel, everything starts with money and ends with money. It's very simple.
True. Yes. Yeah, very wise words. Also, in the meantime, I don't see any additional questions in the chat, but as mentioned, this paper and with much more further details is available for download, and you can also reach us via the CIMAC organization and have a look at the website of our CIMAC emissions group on the CIMAC page. And also, in case you are planning to attend SMM next week in Hamburg at the VDMA booth, which will be together with CIMAC, there will be also a session about this paper on Thursday. It should be the 8th of September, I believe. Okay, as still no other questions, once again, thank you, Johan, for this nice presentation. And I would like to thank all of you for your attendance and the questions, and hand over back to the CIMAC for final words. So, Mr. Schinke, we can see your screen. Thank you.
Thank you very much for guiding us through the session today, Mr. Peitz. And also thank you to all of our speakers for the interesting presentations. Now I'd like to finish today's session with some closing words. As usual, I want to hint towards the upcoming Power2X conference, where you can learn the latest information from experts in the hydrogen field, And I, of course, want to hint towards the next Tech Talk, which is going to be on September 13th. And we will have another session about emission reduction with probably 5 additional presentations about this topic. With that being said, I want to close this session for today and thank all of our audience for participating in today's Tech Talk special. Have a nice day all together. Goodbye.
Thank you. Goodbye.
Thank you. Bye-bye.